question on fractals here. So we're going to take a horizontal line and split it into this shape here, and then take every other horizontal line and do the same thing. Basically, keep repeating that process. And we could even look at the limit as n tends to infinity, which we'll be doing later on. What we end up with is actually something called a self-similar mathematical structure. So if you zoom in on this bit, it would look actually like the whole thing here. Um, and yeah, as you create more and more, you just basically get it looking like itself as you zoom in, as n tends to infinity. So we're we're told, well, this length is going to be 4 because the, yeah, 0 0 to 4 0. This one is going to be 5 because I'm just adding up 5 lots of 1. We're asked in part A to show that the length of L2 is 23 over 4. So what I can see is that I've got a 1 and a 1 here again. So length, I shouldn't say L2 equals, length of L2 is going to equal 2. And then I just need to count up all the little smaller lines, which are now a quarter of 1. So they're each a quarter in length. So 1, 2, 3, 4, 5. But actually, there's going to be 3 lots of this 5 lots of a quarter because I've got 5 here and 5 here as well. Of course, you can count them if you prefer. So that is going to give 2 plus 15 over 4. Now 2 is actually going to be 8 over 4, which gives us our answer of 23 over 4. Good. Okay, part B asks us to write down the number of line segments in Ln that are parallel to L0, so horizontal line segments. Well, we can see in L1 there's 3, and then in L2, actually every single time the process occurs, any horizontal line segment is split up into 3 new line segments. So that one there splits into 3. This one up here splits into 3. So I'm basically going to be times in by 3 every time. And if you look at L3, the same thing happens. Now you take like this one here, and we get 1, 2, 3. And so the result is that, well, in L, okay, I think it's maybe worth writing it down. 3, 9, 27. It's going to be 3 to the power of n. Not have to show, like, write down the number of sloped line segments in L2 that are not in L1. So of course we've got this in both, but it's the ones that are not. So actually it's 1, 2, and then we just times that by 3. So it's 6. By the way, this is not really trying to test us in detail. It's trying to guide us onto the later parts of the question where we're going to use some of these ideas. So just be aware of that when you're doing these questions. You might think, oh, that's quite simple, but it's not there really to, baffle you. It's more there to guide you for part C in a minute. And the final part of B asks us to write down the number of new line segments that are created by the n plus 1th iteration. So from L0 to L1, we're actually creating 2. Here they are. And then L1 to L2, I'm actually creating 1, 2, 3, 4, 5, 6. I think it's just worth writing down the numbers to start with, and then we'll try and figure out what's going on. And then in L2 to L3, well, there's 6 here, 6 times 3. And what is going on is that we've showed before, we have 3 to the n horizontal segments in, say, pattern L2. And then that is each one of these horizontal segments is turning in, well, not turning into, but generating 2 non-horizontal segments. So when I've got my 3 to the n horizontal segments here, sorry, 3 squared in this case, I just then times that by 2 to get the new non-horizontal segments in L3. And what I'm trying to say then is the new slope segments is going to be 3 to the n times 2. So Ln has 3 to the n horizontal segments. Each of these is then generating 2 non-horizontal segments in the next pattern, and that is what we're asked for here. So hopefully I've explained that quite well. I mean, you can just follow the pattern 2, 6, 18, but it's also important to justify it and understand where that's come from. Okay, hence find the length of Ln as n approaches infinity. So I personally think it's a good idea here to just write down the lengths and build up. So L0, the length is just going to be 4. L1 was 5. I already obtained that one. Or maybe I'll look at now how we actually generate it though. So from L1, we're going to have 3 lots of 1 plus 2 lots of 1. And for L2, I know we found the answer before was 23 over 4, but let's just see if we can generate it, in a careful way that we can then use for L3. So we're going to get the 2 from before, and actually that is now going to occur in every single pattern. And then I've got, remember, 3 to the n horizontal segments. So it's going to be 3 squared, and then I'm timesing by a quarter. So that will give me all the horizontal. And then just finally, I need to work out, so I'm separating it now into, right, we've got this 2, we've got these horizontal parts, now I just got the sloped parts. So then it's going to be 2 times 3 times a quarter. That's 6 that we got, but it comes from 2 times 3, because remember it's 2 times 3 to the n. Okay, and that, remember, was equal to 23 over 4. I'm not really interested in what they all equal at this point. What I'm actually interested in is generating this pattern as n increases. Now let's deal with L3 before we generalize. So we're going to have the 2 from here. And now I've still got these little slopes as well. And that actually comes from the 2 times 3 times a quarter. So this term remains basically. And then let's deal with the horizontal slopes. Remember, we've said that there are 3 to the n horizontal slopes. So it's going to be 3 to the 3. And this time I'm going to be times by a quarter squared. That is going to deal with all these horizontal slopes. And then I just need to look at the new slopes that have been generated, and the new sloped line segments created by the n plus 1th iteration. And remember, that was 2 times 3 squared, because it was the previous number that we used to go from, let's just come back up here, to go from n to n plus 1. Actually, we used 3 to the n here, so that's why it's 3 squared. And then I'll be timesing that by a quarter squared as well, because these new lengths have the same length of those horizontal ones. Okay, just take a moment and make sure you've got your head around that. I'm just going to go through it one more time before we generalize. So we've got the red ones, that's worth 2. We've got the purple ones, that's the 2 times 3 times a quarter from before. So those remain, and they'll remain from then on in every pattern. And then we've got the new horizontal slopes, there's 3 to the 3 of them, and now they're each of length a quarter squared. And then we've got the new sloped segments, which comes from having, well, there's 2 times 3 squared of them, and again, they're the same length, they're a quarter squared in length. So that's it. I'm not going to work that out, because now we're going to try and generalize, and because remember, we're actually trying to work out what's going on as n approaches infinity. To be fair, before I do that, I'm just going to give L4 a go, and then we'll generalize. So L4, because this will check if the pattern's working, and you could like draw a little picture of it and tell yourself that yeah, this has definitely got to be okay. So we're going to have 2 times 2 times 3 times a quarter. That comes from the red and the purple. But this time we're still going to have these horizontal slopes, 2 times 3 squared times a quarter squared. It's this term that's now going to disappear and become 3 to the 4 times a quarter to the 3. because I've got an extra, so I'm now another, I have to times it by 3 basically, these horizontal segments, and they're all becoming 4 times as small. And then I just need to think about the new line segments, which is going to be 2 times 3 cubed times a quarter cubed. Okay, right, I think we're ready. So ln is going to be 2, sorry, I wrote times there, I meant plus. 2 plus 2 times 3 times a quarter plus 2 times 3 squared times a quarter squared plus 2 times 3 to the 3 times a quarter to the 3. And it's going to carry on like this. And the next one will be 2 times 3 to the 4 times a quarter to the 4. And then we would keep going with this until the very last one will be 2 times 3 to the n minus 1. Like you can see here, we're using, for L4, it was 3 to the 3. So in general, we take our n and we just minus 1 from it. And it'll be a quarter to the n minus 1. And then finally, I just need to add on these like horizontal segments, which is going to be 3 to the n times a quarter to the n minus 1. That is my length of line ln. I could write this as in sigma notation. I'm not saying you have to for this question, but it does work out quite nicely. So we're actually just summing, forget the 2's for the moment, we've got 3 quarters plus 3 quarters squared plus 3 quarters cubed and so on. That's going to be our term inside here. And it will be going from, let's say I equals 1 up to n minus 1. And then this is being raised to the power of I. But remember, I have to then double each of them. So that will give me, when I is 1, we'll get 2 times 3 quarters. That's this first term here. Let me point an arrow at it. And then it'll be 2 times 3 quarters squared. That's this second term, and so on, up to the very last one, which is here, 3 quarters to the n minus 1. Don't forget, I then just have to add on 3 to the n times a quarter to the n minus 1. Do even better than this because you can actually absorb this term into the summation because it's 2 times 3 quarters to the 0. I could also just realized, so I could write this as 3 quarters to the n. So that's 3 to the n times 1 over 4 to the n. I would just have to then times by 4 to offset that. So it's getting a bit neater. By the way, you don't necessarily have to do all of this. And when I did it originally, I just kind of wrote it as almost as an infinite summation straight away. We could also, by the way, one last little bit, if you want to have, say, I, or let's call it j, as 1 as your first term, then we can just slightly change the summation to j minus 1. And then we can sum from j equals 1 to n. Okay, but that is a pretty neat way of writing down the length. The most important bit, though, what we're asked for, is to look at what happens as n approaches infinity. So as n approaches infinity, the length is going to approach to infinity. This bit here is actually going to, this bit here is just going to become 0 actually. 3 quarters to the infinity is 0. So maybe I should just, I don't know what I'll do. I'll write the limits as n approaches infinity, which disappears. So we're actually left with a geometric series when j is 1. Sorry, that's meant to be -1. I'm sorry, I'm making little mistakes here, but I think I'm correcting them okay. So I'm going to get 1 plus 3/4 plus 3/4 squared, etc. And this is a geometric progression with a equal to 1, common ratio 3/4. So sum to infinity is going to be a over 1 minus r, which is 1 over 1 minus 3/4, which is 1 over a quarter, or 4. So we get 2 times 4, which gives us an answer of 8. The length is actually going to approach 8. Okay, cool. I hope you're happy with this so far then. So we've got this fractal, we've worked out the length of L2, we've then worked on part B, which helped us ultimately write down the nth term for the length of the line. Like I said, I think you can avoid doing that if you can just spot that you're basically, it's going to turn into an infinite series. But if you want to write it as neatly as possible, then this is looking pretty good, I'd say. And then let n approach infinity, find the summation of the infinite series, the infinite geometric series. This gives us our answer of 8. So it went 4, 5, 23 over 4. So it's going to keep getting bigger, but it's going to then, it doesn't get larger than 8. Actually, quite often with fractals, you end up with these infinite lengths. Actually, you can get these structures that have a finite area, but an infinite length. But not here, in fact. The way it's been constructed, we get a finite length, which is quite nice. There was an AEA question, I think, many years ago that I'm just going to pause and look it up actually. Took me a little while, but I just found it. It's question 5 from 2007. Have a little look at that one because it works out in a similar sort of way. It'd be good practice if you enjoyed this question or if you just want to do a little bit more on these kind of scenarios. So yeah, check it out. Right, let's move on to the next part, the area enclosed. I'm going to bring this down to help. So we're told that the area enclosed between L0, the horizontal line, and Ln is AN. So for example, this would be A3. Find the value of A1. Okay. Now we know that this length is 1, and this length is 1, and this length is 1. I'm going to just draw a dotted line along here. So that means we can draw a vertical line down here, and therefore we have a triangle. If I draw it over here, so the triangle is going to have a length of 1 here. Now note also that the whole way across is 4. So at the moment I've gone 3 across, so therefore this must be a half, as must this be. So here's my triangle, my blue triangle, and I can see that the hypotenuse is 1 and the base is a half. Right angle here. So that means I can find out my angle. Cos theta, you might straight away be able to see that this is half of an equilateral triangle. So it's going to be 60, but if not, then cos theta is a half and theta is 60 degrees. Okay, so that means I can work out the height, and sine of 60 is going to equal I could also apply Pythagoras at this point to be fair, but okay, I'm going with it now. H over 1, so H is actually going to be root 3 over 2. And that means the area, this is a trapezium, is going to be a half times the 2 parallel sides, so added together, so 1 plus 2. Remember the general formula for any trapezium like this is a half A plus B times H. So for us, this halves 1 plus 2 times by root 3 over 2, which gives 3 root 3 over 4 is our area of A1. Find in terms of n an expression for an plus 1 minus an. Well, what is happening, let's just look at L1 to L2, is we're creating new trapezia. In this case, we're creating 3. In this case, we're creating, it's going to be 9. So it's going to be 3. So um, we create 3 to the n new trapezia. So L1 to L2, we create 3. L2 to L3, we create 9. And then, we're going to be squaring again. It'll be 27 for the next one. Let's just try and understand the dimensions then. So going from L1 to L2, we create 3 new trapezia, and the top length here is going to be a quarter. L2 to L3, we create 3 squared new trapezia, and the top length would then be a quarter squared. So to go from an to an plus 1, we're going to have 3 to the n new trapezia, and this length here is going to be a quarter to the n. And therefore the an plus 1 minus an is going to be 3 to the n, because that's how many trapezia we are generating, multiplied by 3 root 3 over 4, because that is the area of a trapezia with length 1 at the top, but the length is not actually 1 at the top, it's a quarter to the power n at the top, so that's my length scale factor. Therefore, my area scale factor, I need to square it. Like if suddenly my trapezia was 2 in length at the top, then the trapezium would be 4 times as big. I would square the length scale factor. I do exactly the same thing here. Quarter to the power of 2n, I can write. So let me write it as 3. Okay, and actually a quarter to the power of 2n is the same as 1 over 16 to the n. So 3 over 16 to the n multiplied by 3 root 3 over 4. Okay, sorry if I'm repeating myself. I just want to quickly again explain where that comes from. So we've worked out the area of the trapezium from of A1. We worked out that it's 3 root 3 over 4. Every time we go from an to an plus 1, we're creating 3 to the n new trapezia. So I'm going to multiply 3 to the n by the area of that original trapezium, except that I have to also times by the area scale factor to scale down the area, and the length scale factor is a quarter to the n. Hopefully I've convinced you of that. So we just square it, we times it all together, and it works out quite nicely. We can simplify it to this. So I feel like that bit is probably harder than the length bit to get your head around, but actually the next bit, once you've got it, is not so bad. Is the dealing with the length as n approaches infinity. So A1 we've already worked out is 3 root 3 over 4. A2 is then going to be that exact same amount, but I'm adding on 3 over 16 multiplied by 3 root 3 over 4. I'm just applying my result from part E. And I'm just going to keep going. So A3, I'm going to have exactly the same thing. And then I'm going to times by 3 over 16 squared. And at this point, I think we can see that we can just factorize out that 3 root 3 over 4. And we're creating another geometric series rather. So AN is going to be this 3 root 3 over 4 and the last term is going to be 3 over 16 to the power of n minus 1. Nice. And then as n approaches, I could write this in summation notation. I'm not going to do that here. Um, it's actually going to be a little bit simpler than the original one. Okay, but as n approaches infinity, an will then approach 3 root 3 over 4 multiplied by b again. A is 1 over 1 minus r, so 1 minus 3 over 16, which is 3 root 3 over 4. Here I'm going to get 13 over 16, so 1 over 13 over 16, or 1 or 16 over 13. I can rewrite that as. The 4 and the 16 are going to partially cancel, leaving me a final answer of 12 root 3 over 13. Awesome. Okay, we're nearly there. Well done so far. Keep going. Okay, finally, the same construction as described is applied externally to the three sides of an equilateral triangle. So let me apply the process. We start out with this length of, well, now it's A, and we'd split it up so it looks a bit like this. And we do the same on the other sides. And then we would repeat that process. So over here, we end up with this. That bit stays the same. And, and on the other sides, and then basically carry on. Okay, and we're given that the limit of the resulting shape is 26 root 3. Right, first of all, let's deal with the triangle, I think. This is an equilateral triangle, so area of triangle is going to equal half AB sine C, so half A squared sine 60. Sine 60 is root 3 over 2, so it would be root 3 over 4A squared. Now let's deal with A1 in this case. So this time the length is A, which means that this is going to be A over 4. So again, I can use my length scale factor. I've got 3 root 3 over 4 from the area of the trapezium from before, but now I times by my length scale factor squared. And that means I can do a similar approach with A infinity. I'm going to call it A infinity now. It was AN as n approaches infinity. And remember, we just showed that that was, I think it was 12 root 3 over 13. And then I'm going to be timesing that by the same length scale factor. Okay, so the total area is going to equal root 3 over 4a squared, a triangle, plus 3 lots of 12 root 3 over 13 times a squared over 16. I'll just multiply that out. And then we're told that that is equal to 26 root 3. So I can divide through by root 3. Brilliant. That gives me, maybe I'll times through, well, let me just write out again. So we've got a squared over 4 plus um, 3 times 12 over 13 a squared over 16, that is equal to 26. I can cancel out somewhat here, so that becomes 4 and that becomes 3. I'm going to times through by 13 and by 4. Let me do one. Actually, let me times through by 4 first. So a squared plus 9 over 13 a squared is going to be 26 times 4. 13a squared plus 9a squared is going to equal, now 26 is also 13, so I could write it as 2 times 13 squared times 4, or 2 squared. So 22a squared is equal to that. So a squared is, I can divide through by 2 actually, so that becomes 11, and that just goes. A squared is going to be 13 squared times 2 squared, all over 11. Therefore, a is just 30. I can square root each of them separately. 13 times 2, 26 over root 11. All right. Oh, that was quite involved. It took me a long time making this video, but I hope this is making sense and that you enjoyed this question. Very well done. Keep going.